Okay, there are several aspects of the course we want to think about. We'll start with equation solving. You have linear equations. That's just an example of a linear equation. I'm not going to explain how to solve this. I assume everybody knows how to solve it. You just use the distributive law. Pull all your x's onto one side and your numbers onto the other side. Okay, that's a pre-calculus topic. But I'm not going to solve this one, but just to emphasize an important aspect of problem solving. Let's say you have 7 over x plus 3 equals 4 over 2x. Let's make that 5 over 2x because 4 over 2x would reduce. Okay, what do you do with this? You multiply by common denominator. You do x times 7 over x plus 3, 2x, sorry, equals 2x times 5 over 2x. 2x being the obvious common denominator. If you've got 2x, then you've got the x. Okay. So that gives you 2x times 7 over x plus 2x times 3 equals now I'm just going to go ahead and write it out. 2x times 5 over 2x. Be sure we know what we're doing here. We write this as 2x over 1 times 7 over x plus 6x equals 2x over 1 times 5 over 2x. Yes, what kind of day this was? That's harmless. Okay, and we see x as a factor. Well, okay. If we multiply this out, now you can shortcut this. You could rewrite this, by multiplying the fractions, numerator times numerator, denominator times denominator. And you would get 14x over x plus 6x equals 10x over 2x. Now, there are a lot of ways you can do this. You could have known that this x is going to divide this x when you get done multiplying everything out, as it will here. Okay, so you kind of skip these steps if you're really sure of that. Thing that I want people to avoid is just crossing things out and thinking that they're canceling, because people don't seem to understand. A lot of people don't seem to understand that you have to have a factor in the numerator that cancels with the same factor in the denominator. That's the rule. It works because of this, okay? So you can actually isolate this as x over x times 14. X over x is 1. So this gives you 14. I just say the x divides out. If you cancel, be sure that you are canceling according to the rules, which is factor the denominator into factor the numerator. Then it works. Okay, then 2x divides into 10x 5 times, right? Or you can see the x divides the x and the 2 divides the 10, that gives you 5. I'm not going to take valuable class time in the last week to solve that problem. You know, you got to subtract 14 from both sides. You got to get 6x equals -9. And then you divide both sides by 6, you get x equals -9/6, which is -3/2. And then you take it back in here and check it. All right. So this does give you a linear equation. Now, the next type of equation is a quadratic equation. Let's do the same numbers we used here. Except the 5/2x, I'm going to put the x in the numerator, 5x/2. Okay, so the common denominator is 2x, right? So we want to clear the denominators. Anytime you got denominators in a fraction, clear them out. Okay, now one thing I'll say before we go on, and Open Math has told you this, and you want to make note of it, that x equals 0 is excluded from solutions of this equation, because if x equals 0, you have zeros in the denominator, so that the equation is meaningless. Okay? So, but when you solve this problem, you're not going to get 0 anyway. Sometimes, though, you have a situation where 0 would be a solution if you didn't exclude it at the first step. So anyhow, common denominator, 2x, multiply 2x times 7/x plus 3 equals a plus equals 2x times 5x/2. And you get 2x times 7/x. I'll put a few dots here. I'm skipping a step, but you're going to get 14x/x plus 6x equals (10x²/2). Then the x will divide the x here, giving you 14 plus 6x. The 2 will divide the 10, giving you 5, but then you have 5x². Now, at this stage, many people will try to eliminate x, get all the x's on one side, but you have an x term and an x² term, and it isn't going to work. You can't use the techniques that work for linear equations when you have a quadratic equation. So you say, we got an x, we got an x², and we got a number. Okay, those three things. So it's quadratic. We put that into the form ax² plus bx plus c equals 0. Okay. And we just do that by getting everything on the same side. So we add a -5x² to both sides, which will make this side 0. Okay. So this side is going to be 0. In this side, we could arrange to give you negative 5x squared plus 6x plus 14. Now we use a quadratic formula. And I'm not going to do that. Everybody knows how to use a quadratic formula. If you come into the exam not knowing the quadratic formula, not knowing how to use a quadratic formula, then you're not as well prepared as I think you're going to be. Okay. Now I'd say use the quadratic formula. You could try to factor this, but I think it's going to be likely to be hopeless. We'd have to be combining 5s and 1s and 14s and 7s and 2s and stuff. So there might be a way that factors, but you don't want to mess with it. Okay. All right. So that's basically it for quadratic equations and equation solving. Now, this doesn't look like a quadratic equation when you start it. But if you follow the advice I give you, which is to always, if you have denominators, find the common denominator, preferably the least common denominator because it's less work, and multiply both sides by that common denominator, you're going to get this equation here. Well, this equation, you're going to recognize that it's quadratic and can be put into the form ax squared plus bx plus c equals 0. Okay. Another thing I would do to this, maybe, wouldn't really matter, but I might multiply everything by -1 to change all the signs here and get 5x squared minus 6x minus 14. Because you kind of want to have a positive here, but that's really not a big deal. You're going to have, as long as you substitute the numbers, it's going to work out. Okay. As long as you substitute correctly in the quadratic formula and simplify it. All right. Polynomial equations. First of all, if you have an equation like this, where the polynomial is factored, and you really have almost no chance of solving a polynomial equation unless it's factored. And you have the theorem in precalculus. We've talked about it a little bit in this support course. You can always factor a polynomial. Well, a polynomial always factors whether you can figure it out or not into linear terms. Because if I set this equal to 0, it's going to be a linear equation, right? Or quadratic terms. Okay. If it factors down into quadratic terms, you can use a quadratic formula to see if you've got zeros. In which case, it actually factors into two factors. If you got zeros, if your quadratic function, if your quadratic expression, if your quadratic factor set equal to 0 gives you solutions, then it actually factors. I'm not going to get too technical about that. But you want to factor it down to where you've got linear and quadratic terms. And if you do, you can solve it. So This breaks down into, by the zero property of multiplication. If you're multiplying three things and they give you zero, then one of them's got to be zero. At least one of them's got to be zero. Usually just one. So you got 3x plus 12 equals 0, or 2x minus 4 equals 0, or x squared plus 6 equals 0. So we solve this. We get x equals negative 4. We solve this. We get x equals 2. And we solve this. I'll write D and E. The solution to the x squared plus 6 equals 0 does not exist. Now, you can put this into the form of quadratic. Ax squared plus bx plus c equals 0. A would be 1 because A is the coefficient of x squared. B is 0 because you don't have an x term. And C is 6. And you plug it into the quadratic form and you get the square root of negative 24. Under that, your b squared minus 4a squared is negative 24, and you can't do the square root of negative 24. That's fine if you do that. Even better, you can reason it out. X squared can't be negative. If you add a number that can't be negative to 6, you ain't going to get 0. The only way this would have a solution is if x squared is equal to negative 6. Okay? X squared can't equal negative 6, at least not among real numbers. So your solution set is negative 4, 2. Now, while we're at it, I'll make a little plug for graphing quadratic function. Okay? Okay? At x equals negative 4, I like to draw a vertical line, vertical dotted line, so I can label it down here where the label's going to be out of the way instead of putting the labels on the x-axis. But that's your option if you want to draw lines through numbers on the x-axis because that's where your graph goes. I'm okay with it. I can tell what you're doing. Okay, but for construction, I kind of like to do this. But that's optional though. In my course, I'm not going to give you a grid to graph on. I expect you to be able to graph it by hand. I think you learn a lot more that way without having to think through, without having a grid there to prevent you from thinking about things you need to think about. Okay. There's an alternative argument on that, and I respect it. So I don't make any comment on what anybody else might do. But anyhow, okay, so we have zeros here. We know that the graph has to go through these points. Another thing, by the distributive law, at some point, this 2x is going to get multiplied by the x squared, right? I mean, if I do distributive law on this, I'll have 2x times the quantity x squared plus 6 minus 4 times the quantity x squared plus 6. So I'll have a 2x times x squared out of that. And then when I multiply this, I'll have a 3x multiplied by that. I said I'd have a 2x squared. I have a 2x cubed out of that. 2x times x squared is 2x cubed. And then 3x times that is 6x to the fourth. Okay, well, this then equals 6x to the fourth plus lower order terms, okay? Just powers of lesser degree. Well, when x gets really big, those powers of lesser degree don't add a hill of beans. What 6x to the fourth gives you, okay? If x gets big enough, means when you zoom out on this graph, what you're gonna see is basically just a 6x to the fourth function with little wiggles in the middle. And we're looking at the wiggles here. 6x to the fourth is an even power function. X to the fourth is always positive, or it's never negative. It could be zero. If x is zero, it's going to be zero. But it's never negative. It's a power function. So we just make a little sketch here. Six x to the fourth is going to look like this. And the function that we're trying to graph, this one, is going to be practically exactly the same as 6x to the fourth, except it might wiggle a little bit in here close to the origin. Okay, so you got the 6x to the fourth, and you got the p of x function, which varies only here by some wiggle, graphing the wiggles. And noting that if we move to the left, as soon as this thing's done wiggling, it just takes off in the positive direction. So it goes up this way, and it's going to go up this way. Going to open like so. Okay, so it's going to come down very fast. It's going to go through this point. It's going to come back up through this point. Now, whether it, well, the way it goes down, we want to get the y-intercept. If we get the y-intercept, then we know whether it's below or above the axis down here. So what's the y-intercept? Well, the y-intercept y-intercept occurs when x equals 0. This function is p of x, so I'm just going to make an abbreviated statement. This y-intercept is at y equals p of 0. In other words, plug 0 in, let x equals 0. So if x equals 0 and we plug it in, we're going to get 3x plus 12. Well, any of the x terms are all going to be 0. We're just going to be left with 12 times negative 4 times 6, okay, which I think is negative 196. Let's make sure about that. 48. No, I'm sorry, that would be, okay, it's going to be 72 times 4, negative 288. Multiplied by 4 twice. So there's a y-intercept. Now, it's going to be unclear, and unless you've had calculus, you won't have the tools to figure it out. Given calculus, you have the tools to figure out where the thing is lowest, and maybe there are even relative minima there or something. So it could look like this. Or it could look like this. You could do all kinds of things. You just don't know. Okay. There's also a theorem that I'll just mention. It tells you how many wiggles a function can have. You know, if you have a quadratic function, it's got a parabolic graph. I'm going to call that, it doesn't wiggle. It just comes down, goes back up. Now I got my printing all messed up there. Didn't get all the letters of turning in here. Has one turning point. Okay. Cubic function. Okay. Now this cubic function has no turning points, but a cubic function can also look like this. No more than two turning points. You know, I say now that that means it's got to go down and then back up, or it's going up and then down and up. I call that a wiggle. Okay. I'll do it down here. Okay, this is degree 3. This is degree 2. Degree 4. Degree 4 can look like this. It's a lot like a quadratic, but it's flatter toward its vertex. Okay. Or it could look like this. Or it could look like this. no more than 3 turning points. Okay. If it looks like this, where all the turning points and everything that happens around the turning points is below the x-axis, it's only going to have 2 zeros. But if I add the right number on the end of that function, it's going to vertically shift that graph, right? If I add a number k, it's going to shift the graph vertically k units. And if k is just right, it could be like this. So we can say that it has no more than 4 zeros. Now that's counting multiplicity. And again, multiplicity means if this was squared, well, then I'd have degree 5, okay? One of these is squared, but I'd have a quadratic zero. Talk about that a little bit. I'm digressing from equations into polynomials, but it's a natural digression. So we need to talk about that. I was going to talk about it separately, but now I'm into it. So I'm going to keep talking about it for a minute. Then we'll come back to exponential and logarithmic equations. Okay, so we have no more than 4 zeros here. We could have 3 zeros. You know, notice how on the blue graph, this relative minimum, this low point, is a little higher than this low point, right? I could pull this graph up on another picture. I could pull that blue graph up like so. Okay. That's not exactly the same shape as a blue graph, but you see how that sort of thing can happen. How many zeros do I have here? I have 1, 2, 3. But this zero is a multiplicity too, because in the vicinity of this point, as we've seen, this will act like a quadratic function. Just in a very small interval. It acts much like a quadratic function. In these intervals, without writing so many words, I'll say that it acts linear here and here at this zero and at this zero. And we've talked about that, especially in pre-calculus class. I'm not going to belabor it too much in this support course. You have a rule that says if this thing is squared, then the zero at -4 would be quadratic. It would act like the vertex of a parabola at that point. It would touch the axis. It would look like this. If this was cubed, then it would act like this at the axis. So we could have a shape like this one, raise it a little bit, and you'd have a zero here. It would act like a cube. So that's all I'm going to say about that. You have the rule for multiplicity of zeros and how you construct the graph. So the way I'm telling you right now is the easiest way to see what happens in the long run is to understand what the graph of a power function looks like. If it's an even power, it looks like this. Maybe it's going to be upside down, but it looks something like this. Okay, kind of like a parabola, but flatter. If it's an odd power, it looks like the cubing function. But it's a higher power, it's flatter. And in my pre-calculus class, we did some exercises around that, and I'll probably talk about that in pre-calculus class. Okay, anyhow, that's pretty much what you need to know to graph a polynomial equation. Yeah, I'm going to go ahead and talk about factoring polynomials. I'm probably not going to work through details of this problem. Let's just take 2x cubed minus 5x squared plus 7x minus 4. Okay. And what you do when you see something like this and you think you might want to factor it is you think of easy values of x and plug them in and see if they give you 0. And in this case, if x equals 1, that's the easiest thing you could get. If x equals 1, you're going to get 2 and 7, which is 9. You're going to get -5 and -4, which is -9. And that's going to be 0. Okay. You do long division, x minus 1 into this thing, and you're going to come out with a quadratic, which you can solve. You don't even have to factor it. You have the quadratic formula. So we're going to say, okay, well, multiply 2x squared by x, we're going to get 2x cubed. But then we also have to multiply it by the whole x minus 1. We get minus 2x squared. Make a little reminder sign here. Because we're going to have to subtract this from this, because having 2x squared gives us this much of what we need. Whether you understand that or not, that's kind of what's going on. I don't want to do a lot of explanation there. Anyhow, we get minus 3x squared plus 7x, and of course this gives us 0. And then what do we need? We need a negative 3x. So negative 3x times x minus 1 gives us negative 3x squared plus 3x. Now we're going to add this one and actually subtract this one. And that's going to leave us 4x minus 4. Okay. X will go into 4x 4 times. 4 times x minus 1 gives us 4x minus 4. And we're done. That's 2x cubed minus 5x squared plus 7x minus 4 equals 0. Becomes x minus 1 times 2x squared minus 3x plus 4 equals 0. Well, I'll write it again up here, x minus 1 times 2x squared minus 3x plus 4 equals 0. And what do we do with this? We use the zero property of multiplication. The only way this product is going to be 0 if this is 0 or this is 0. So we get x minus 1 equals 0, or 2x squared minus 3x plus 4 equals 0. It's possible that this factors. I didn't set the problem up so I'd get something that factors, so it's probably chances are that it won't. So I'm not even going to bother trying to factor it. I'm just going to use a quadratic formula, the darn thing. Now, another thing I can do, of course, is I can do the b squared minus 4ac, the thing under the radical. And if we got something we can take the square root of, then we know that it's going to factor over, with reasonable fractions and stuff. Okay, well, anyhow, if I do the b squared, which would be negative 3 squared is 9, and then negative 4ac, a is 2, c is 4, 2 times 4 is 8, and 4 times that is 32, and we're subtracting that because it's minus 4ac. So we're going to have 9 minus 32. It's going to be negative. So I don't even bother doing anything with this. I evaluate b squared minus 4ac. I don't require that you be able to do that. I'm just telling you if you run into one of these and verify that b squared minus 4ac is negative, then you're done. It doesn't reduce. It doesn't factor. Okay? So whether you know that or not, you can use a quadratic formula. So you use a quadratic formula and you get that square root of negative 23 if I did the arithmetic right. Okay. 9 minus 32, I think it's negative 23. And you don't have to evaluate anything else. So the solution to 2x squared minus 2x cubed minus 5x squared plus 7x minus 4 equals 0. Is x equals 1. The solution set is the set that contains only the number 1. So if you want to graph this thing, here's where x equals 1. Zoom out. It acts like 2x squared. So it's going to go up sharply here. It's going to go down sharply here. And the y-intercept is going to be at negative 4. So let's say this is y equals negative 4. It's going to go through these 2 points. It's going to have this sort of shape. So it's probably going to come up. And we don't know exactly where it's going to flatten out. Have to use calculus to figure that out. But maybe it comes up like this, starts to flatten out a little bit, and then goes through these points, goes on up. Okay? That would be a best guess. One warning, there's some open math videos that don't show the cubic function flattening out. It just kind of goes through at a 45-degree, goes through 0 to 45-degree angle. And I can't believe somebody actually did that, but I've done worse. And probably put it on video at some point. Somebody ought to really redo that video. It's very misleading. Make sure you understand that any power function from whole number power over 1 is going to flatten out at 0. And the higher the power, the more it flattens out. That can be important, especially going to calculus. It helps you understand some things about the overall shape of polynomials. Okay, well, I didn't mean to digress all the way into polynomials when we did equations, but there it is. So we're going to go on and look at exponential and logarithmic equations. I'm just debating how to denote this. So I'm not going to try to say what the equation is typically like. I'll just do typical equation like 3 to the 5x minus 7 plus 9 equals, let's make this 4. Okay, plus 9 equals 16. Okay. What we want to do we want to get our 3 to the 5x minus 7 equal to something. We want to get the 3 to the 5x minus 7 all by itself on one side, which is very easy to do. We're going to subtract 9, and then we're going to divide both sides by 4. Okay? And I'll just do that very quickly. We get okay, subtract 9 from both sides, we're going to get 7. I'm not going to write out every step of the algebra, but everybody should remind themselves so you don't lose it later. And then we divide both sides by 4. 3 to the 5x minus 7 equals 7/4. Okay, then this translates into log base 3 of 7/4 equals 5x minus 7. Now, how did I do this translation? I used the fact that b to the a equals c is equivalent to log base b of c equals a. If you have an equation in this form, you can change it to this form. And that's handy if the variable you're looking for is in an exponent. Okay, so there we have it. I'm going to reverse the sides here. It's unnecessary, but I'll do it anyway. Okay, so we just like to have the x on the left side. I'm okay with it on either side. And if you leave it on the right side, that's okay. Okay, so we get it down to the form and very easily. Again, all I've done with this equation is I've subtracted 9 from both sides, leaving me 7 on this side. And then I've divided both sides by 4, which gives me 7/4 on this side. And now I've got that equal to 3 to the 5x minus 7. I use this rule, the inverse function rule, okay, to get this equation. I rewrite it, flipping the sides. Uh-oh. I added 7 to both sides and I didn't write it down. Okay. Okay, now what do you do with this? Well, what I really kind of want to see on your paper is log of 5/4 divided by log of 3 plus 7 over 5. At which point then you're welcome to punch that into your calculator, because you don't know what the log of 5/4 and the log of 3 is. Okay. Now I know the log of 3 is around 0.3. Log of 5/4, I'd have to interpolate something. I don't want to do that this morning. Okay. It's got to be kind of close to 0. But I don't want to estimate the decimals right now. Okay, does that make sense? I mean, that's a review. We've done that. People did well on the homework when we had that, but they probably had this in front of them all the time, rather than doing a few problems with this in front of them and putting it away and pulling it out of memory because you're in a hurry, because you got a life. Okay? It's not the way to learn mathematics with everything you need in front of you. You need eventually to internalize it to where if you now see it in a brief review, you remember it. Okay. So whatever you did, and I'm not talking just to people in this room, I'm talking to people in the distance class and anybody else who's fool enough to look at these videos. That's the way to have done it. And if you didn't done it that way, learn a little bit of a lesson if possible. Do your homework in a way that causes you to retain things. It helps you retain things. Okay, that's pretty much it. Now, there are some twists on exponential equations. We have 2 exponential expressions. And where you take the log of both sides of an expression and so forth. But not going to talk about that. If you can do this, I'm content. And if you can do this and you got a really good aptitude for mathematics, then if you run into the other, which most of you won't, you ran into something just a little more complicated, and you did in homework. People didn't seem to have any trouble with it. Now, I'm not sure. Well, yeah. Okay, so that's pretty much it. Well, I'm going to talk a little bit about what this equation means. If I No, I don't want to do that. We'll talk about that next time. Okay, we want to relate this to graphs and so forth. Okay. And that'll take me a little further afield than I want to go. Okay, logarithmic equations. I'm going to make these log base 4. And over here, I'll have 16. No, I want a little bigger number. Although it's not going to make a lot of difference. How do we solve this equation? I'm even going to get real mean about it and put a 3 in front of this one. Because we want to refresh a little bit on the rules for logarithms. Now, you might be rusty in the rules for logarithms. It's been a few weeks since we actually had an assignment involving those rules. But to refresh your memory, if we do 3 times the log of something, that's the same as the log of that thing cubed. Okay, so the first step is we want a log base 4 of something, not a number out in front, and that number out in front just becomes an exponent. That's the rule. Make sure you review the rules. I'm not going to write down the rules for exponents on your test. Somebody else might, because of course there are students in this course from other sections. Personally, you need to know those rules. You need to understand them. Okay. Then I have a log base 4 of one expression and a log base 4 of another. I can combine those. They're added. So we get the log base 4 of the product of those things. So now we have an expression, log base b of c equals a. The c contains our variable, so we want to change this to exponential form. So this becomes I did something boneheaded here. It's going to make that a small number, decided to make it a big one. We're going to change that 64 to 2. Okay, so a is your 2. We have 4 squared equals 4 minus x minus 4 cubed times x squared minus 9. So we could write that out as x minus 4 cubed times x squared minus 9 equals 4 squared is 16. Okay. Now, to solve this, we expand it and get a polynomial equal to 0. Okay. Then good luck, because you're probably not going to be able to solve it. Okay. It's going to be a polynomial of degree 5. It's probably not going to have any whole number roots or even fractional roots. Probably going to have a bunch of irrational roots. Okay. So you know it's going to, if you graph it, it's going to have a form of a, like a cubic function, but flatter. There are techniques you can use to solve the thing, but in practical terms, nobody ever uses them. Okay. So this just illustrates the process of solving something like this. Now, if this had been 0 instead of 2, well, we still wouldn't have been any good, because we'd still have 4 to the first power. We'd have a number on this side. If the number on this side turned out to be 0, then it would be easy to solve these. You just, x would be 4, or x would be 3, or -3. But we can't get a 0 on this side when we're doing a log. Okay. A log can't equal 0 because of, what do we know about logarithmic functions? Well, they're inverse to exponential functions. Exponential functions have graphs that look like this. They never hit 0. Logarithmic functions are just a reflection, sort of the exponential functions. And this part of the graph here corresponds to this part of the graph here. And this thing never touches the y-axis. So x is never 0 for a logarithmic function. So we could not get a nice polynomial like this times this equals 0 out of a logarithmic equation of this nature. So unless they're contrived, and they could be, you've got to come down to a polynomial equation that you're not going to have much luck solving. Now, if I didn't have the 3 in front of this, and if this was x minus 9 instead of x squared minus 9, then I would have just gotten x minus 4 times x minus 9 equals 2. Well, I can expand that. It's just going to give me a quadratic. I could subtract 2 from both sides. I've still got a quadratic equation, and I can solve that using the quadratic formula. Does that make sense? You want to think about that. You could go ahead and do it yourself. You could write this out without the 3 and make that x just an x, have it set equal to 2, and then do everything I did. You would find that instead of getting a 5th degree polynomial that you're never going to figure out how to solve, you get a secondary or quadratic polynomial. Set it equal to 0 and use quadratic formula. Factor it if possible. Okay. Now, those are the main types of equations that we end up solving, but I'm going to illustrate one more. those come up. And I'm going to do it in terms of a function, much like the things I'm thinking of putting in the exam. Okay. I'm going to put 3 points here. Okay, now I'm going to put a point to the right. You want it to be above this point or below? Just tell me above or below. Below. And I'm going to go to the right. And now I'm going to be contrary and put 1 above. Okay. Now there is a parabola that'll fit these 3 points. Okay. I'm having a hard time visualizing it because of the way you made me do the points. I can try coming down like so. Come down real sharply and go through here, but we're going to miss that point, aren't we? Okay. Maybe I come down like this and down to here and come around and get up through here. That looks like it might kind of work. Okay. So let's go ahead and use this one. Whoops. I want to cross out the other. I'm just going to be sloppy and erase it with my finger. So now I have the quadratic function that goes through my given points. Where's the vertex? Well, where's the axis of symmetry? This is pretty close to the vertex, the way I drew it. Just coincidence of the way it was drawn, okay? But I was kind of compelled to draw it sort of like this. I'll say the vertex, here's the axis of symmetry. Now let's just say that this is a line x equals 1. This is the line x equals 10. What could this line be? Well, x would be between 1 and 10. It's a little closer to 1 than it is to 10. Halfway between 1 and 10 is probably here. Halfway between 1 and 10 is 5.5. So I'm just going to fudge a little bit and say that this line's maybe x equals 5. That's close enough. Keep it in whole numbers so we don't have to get all messed up with fractions. Okay, so we're just looking at a process. Okay, this is the axis of symmetry. Y-intercept is here. Okay, show me with your fingers. What do you want y to be? 7. I was hoping you'd have 7. That's one of my favorites. Okay, y equals 7 here. Okay. So now that we have a scale, we have the vertex, which is here. Okay, if this is a line y equals 7, what's this? Well, how many of these go into 7? I've got 1 here, 2, 3. I don't think it's as low as 1, but I think it's not quite 2. So as much as I hate fractions, I'm going to call that y equals 3/2. So what are the coordinates of the vertex? Okay, so five comma, save the slash for the 3/2. Okay, vertex, 5, 3/2. Y-intercept is 0, 7. Can we get the equation of the quadratic function from this? Doggone right we can. Okay. Starting with the toolkit function. Y equals x squared. We got to stretch it vertically, but we don't know by how much. Now, what we do know, though, is we know that the red dot's going to be right there. And we know that the red dot is the image of the origin. So we know how far we shifted here. We know how far we shifted here. So we know H and K. What we don't know is the vertical stretch, but since we know the y-intercept, we're going to be able to figure out what the vertical stretch is. Stretch vertically. I'm going to put this into the context of our function notation. We get y equals a f of x. Okay. And we'll figure out what a is shortly because we're out of time, but that's going to be easy. Okay. Then we get our y equals a f of x minus h plus k. So y equals a times x minus h squared plus k. Well, that's y equals x minus 5 squared plus 3/2. So we've got everything but the value of a. Using the point you selected, which happens to be the y-intercept, 0, 7. We get 7 equals a times 0 minus 5 squared plus 3/2. So 7 equals 25a plus 3/2. 25a equals 7 minus 3/2. which is 14 halves minus 3 halves, which is 11 halves. A equals 11 over 50. Now, I skipped some steps there and wrote it down fast because we're out of time. But okay, A is 11 over 50. So now our function is y equals 11/50 of x minus 5 quantity squared plus 3 halves. So now we want to find let's say that y here is equal to 4. We can estimate our solutions. Y equals 4. That may be x equals 3 halves. And this is 1, this is 5, this is 10, this is x equals 8. Those are our estimates. Okay, well, solving the equation, which I didn't leave myself much room to do, but I'm going to squeeze it in down here. Solve the equation y equals 4. Well, y equals 11/50 of x minus 5 squared minus 3 halves plus 3 halves equals 4. How do we solve this? I'm going to multiply both sides by 50. And when I do it, I get this. I'm not writing that out. There's a time. So you get x minus 5 squared equals 125 over 11. I just subtracted the 75 and I divided by 11. Those should be familiar steps. Then x minus 5 is plus or minus the square root of 125 over 11. 125 over 11 is about 11. And the square root of 11 is about 3.5. So I'll write the rest out here. Approximately plus or minus 3.5. So x equals 5 plus or minus 3.5. I've got x minus 5 equals plus or minus 3.5. If I add 5 to both sides, I get this. Oh man, my estimates came out pretty good. So these are approximate solutions. That's going to be 1.5 or 8.5. Now, if you want to look at more detail in solving this equation, ask next time. We'll work it out with all the steps, but I think you can figure it out. Okay, so anybody asks, we'll work it out for sure next time. And you notice my estimate here was 3/2. Okay, well, that is 1.5, so I nailed that one, but it's not really nailed because the square root of 11 really isn't 3.5. Okay, it's close, but not really. Okay, and then I got 8.5 here when I estimated 8. So by drawing 3 points, figuring out after just a little confusion where the curve needed to go, estimating the axis of symmetry in the coordinates of the vertex, we got something that actually made sense. Okay. Now I'll probably go over this example in the pre-calculus class. And I'll probably put up another board and do this solution in a little more detail. So you could check that out if you're able to stick around for the class. You can see it there. But we're gonna go in and do something else. Okay, so I'll probably spend a little bit of time just going over these solutions and telling people to look at the video for the support course. Maybe 10 minutes on that, and then we're going to dive into something else. And we can talk about that more if there's something that's not clear in this class next time if it comes up. Okay.